From long-range to short-range interactions, how do particles scatter in Yukawa and delta potentials? Let's break down both cross-sections step by step. And here we see a great animation from the Mathematica notebooks about the scattering process, and being able to visualize this is not always the easiest thing. But for us, we have a 2-for-1 today. Problems 12 and 13 from Chapter 10. In 12, which is just a continuation of 11 from the last video, we now wish to calculate the total cross-section for scattering from a Yukawa potential in the Born approximation, and then express your answer as a function of E. Then in 13, for the potential in problem 10.4, which was the delta potential, again shifted, calculate the scattering amplitudes, differential cross-section, and the total cross-section in the low energy Born approximation. B. Calculate the scattering amplitude for arbitrary energies in the Born approximation. And then C. Show that your results are consistent with the answer to problem 10.4 in the appropriate regime. And this is kind of why we like this part of the question, why we want to do these all together, is because we want to verify these results from these approximation schemes. And regardless of whatever scheme we use, we want to make sure that we're talking about the same physical phenomena and same physical observation. Otherwise, why create so many things if they don't relate to one another and actually give us some credence to what we're doing? But with these processes, it can definitely be hard to see and kind of have an intuitive feel for what's going on. So Mathematica has a couple good notebooks, and so does some of the Python libraries. But how else can we visualize this? The reason why is because scattering is such a well-known phenomena and a well-studied phenomena, and on top of that, it's used almost everywhere in terms of experiments. So utilizing this and building an intuitive case for it would be very helpful. So let me know what you think would be best to try to help visualize this, because I think it would be very useful to us. Moving forward, there's a lot of algebra in this thing that it's just not going to make into the video, but if you want all the algebraic steps and all the tedious work, feel free to grab the PDF from Patreon, or I can just send you the link if you comment that you want the PDF below. No big deal. If you're curious about the world of science, be sure to subscribe. I post educational content every week to quench your thirst for curiosity. So with that, let's break down problem 12. So, heading us straight to stop number 1 then, this is a continuation of problem 11 where we find a total cross-section from the scattering amplitude in example 10.5, and that we verified in 11. Now we need to set up the differential cross-section, okay, and that was pretty easy thanks to the likes of equation 10.4 or 10.14. And what we see is that we just need to square the magnitude of the amplitudes, and that's pretty easy. Now, we see here that we have a theta here, but this does not look to be theta dependent. But we have to recall that this kappa in green down there, thanks to equation 10.89, brings us back into the angular dependence that we often forget about with the regime. And that's thanks to 2k sine of theta over 2. So now our whole goal is just to make this tidy and clean up from the algebra. And what we see here is that we're trying to get this mu out, and the reason will become will be elucidated very soon. But we want to clean this up for the sake of what we have to do with finding the total cross-section and integration. So let's just we're multiplying this by 1, but the 1 we have is mu squared over mu squared. So we could factor out a mu squared from both terms. And in doing so, we have our mu squared out here, but because we have a square bracket, we need to square the mu squared. Now we can put that mu squared into the coefficients here, since that was a square as well. And then we see that we have a square coefficient, square sign. So put them back together, simplify the mu over here, and we get our differential cross-section. Now, given that we have the differential cross-section, we need to integrate this with respect to the solid angle. Thankfully, we can verify this with the equation 10.14, integrate out, separable differential equation, pretty easy. And then we have to integrate over what we call the solid angle, which is just the angular part of the 3 volume for the spherical coordinate system, so that's not too bad. But now we need to actually plug it all in and simplify, which is not going to be an easy task, so buckle up and get the algebra minds working so we can simplify it. Alright, so since the solid angle has our theta and phi dependence, we know that phi runs from 0 to 2 pi, as indicated in blue, theta 0 to pi, as indicated in green, and we see that we have our green, 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 all thetas, phi's in blue. We note that we have a ton of constants here, so let's bring them out front. We also note that our limits of integration are not dependent on the other variable, so we can push them out front, no big deal, and separate them thanks to Fubini's theorem. Pretty good there. Then once we separate everything, get it all calmed down, we realize that we have a problem with this theta integral. Okay, and the difficulty here is noting that the arguments of the sine function, because we have a theta over 2 here and a theta. Now, this term in the differential element from the solid angle has an angle that is twice that of the angle in the denominator from the scattering amplitude, as we see that's the relationship. As a result, using the double angle identity will be beneficial. So we take the sine theta, write in terms of the double angle identities, and now we have everything in terms of theta over 2. And that will set us up for quick success, all things considered. Now phi, we don't have any dependence, so upper limit minus lower limit leaves us with 2 pi. Easy enough. And once we get done with both of these, we now see that with the substitution of 2, we will be set up for success. So here's the substitution from the PDF. If we let u equal the argument squared in the denominator, so 2k over mu sine theta over 2, and we just find its derivative, no big deal. We see that we get k mu cap or cosine theta over 2, easy enough. We solve this for what we have inside, which is 2 sine theta over 2, easy enough. Then we solve this for du for the cosine, so we're good to go. We can get rid of the sine and the cosine from the differential elements and clean up the denominator there. But also note that we could change the limits. Go ahead and do that anytime you have a substitution, so you don't have to back sub or resub. Now once we do that, we're good to go. So let's see how we apply it. So very quickly then, we see that we are cleaned up the integral quite a bit. We get a u down there, square. Then we have our sine theta over 2 substitution there. And then the du with the cosine in it right there. So we got rid of everything. We note that mu and mu here are going to simplify down and cancel with 2 of those factors. Hence you have a mu over 2, or mu squared here instead of mu to the 4th. K and k come out. We make a k squared there. So we're good to go. Limits are changed, so we're good there, simplified. And now this integral is definitely easier to address, but another substitution would make this antiderivative extremely evident. And we see here that if we let t equal this denominator, then dt is pretty easy. Take that over, solve for what you have inside, which is a u du. Go ahead and highlight that just because it's easy. U du, we can substitute out, easy enough. And then of course change our limits. Why go back and resub when we can just change and evaluate? So after that, we plug everything in. This 2 and 1/2 cancel, easy enough. And now we see that this is just 1 over t squared. Or you can write this as t to the negative 2 power, which then the integration power rule comes in. And we see that we add 1 to the power, divide by the new power. Now, that's not too bad, all things considered, especially at this level. We just have to keep track of this darn negative sign. So we put it out front here. T to the minus 1 power is 1 over t. Now we just have to evaluate an upper limit minus lower limit. Well, you see that this minus 1 here, since we have a fraction here, is going to be a problem. So we keep it color-coded red so that we can find a common denominator and add them across. Now, here's where the algebra becomes overwhelming at some point, and to what level of simplification you might want. But of course, we have to distribute this negative sign into both of those components and simplify. So 1 minus 1 goes away. Then we're left with the negative left over here and out front. Cancel, cancel. Easy enough. Now what to do with all of these constants? It's not really, evident to us to what level we need to, but since we know eventually we're going to have a lot of cancellations, let's just go ahead and tidy this up. So we see that we have a mu squared, k squared here, which is going to multiply this denominator thanks to the fraction rules. But upon doing so, we see that we get a k4 over k squared mu squared here and here. So what can happen then is that this 4 can be broken down into a 2 squared, and this mu right here can be a mu squared as well. And these two will eventually end up here, but what we notice in writing it like this is that k squared cancels, and this mu is going to go into simplifying this thing so we don't have a fraction in the denominator itself. So instead of trying to combine these mu's again, we want to simplify this fraction. Fair enough. So like I said, this 2 and this mu, since they're both squared, can join forces in this set of constants. Hence 2 and mu right there, color-coded blue. Now we just distribute this mu into here. We see that upon doing so, cancel, easy enough. But since we want this written with respect to energy, we need to recall what the wave number is because that relates k to e and thus e to sigma, the cross section. So knowing that we have k squared equals 2me over h bar squared, we're now done here, simplified across. So really not too bad, but if you want to simplify this more to get rid of this h squared here, h bar squared, excuse me, you can maneuver that with algebra, which I did in the PDF. At this point, I think we're losing track of the overall scale of the question by doing so, but it is available for you if you'd like. And if you're finding this helpful, don't forget to give it a thumbs up. It helps more curious minds like you discover this content. And with that wrapped up, we now complete number 12 from this, and we can move on to 13. And right on schedule. In 13, we want the low energy approximation, and so we need to evaluate the equation 10.80 to find the scattering amplitude, which will lead us to everything else. So plugging in our potential from 10.4, problem 10.4, excuse me, is the delta potential with some constant alpha, and now we just have to run this through everything else. Easy enough. So delta here, then our differential element, we see we get a lot of r's there. Split everything up in terms of their dependencies, thanks to Fubini. Again, color coding makes that work pretty easy. We see that phi gets there, sine goes to negative cosine, so our negatives cancel, beautiful. And then we have the shifting property of the delta that we have always talked about. So shift that, and we need to evaluate r squared at r equal a, so the shifted value. And we're just left with 2 pi minus 0 from this. Cosine pi minus cosine 0. That'll simplify pretty quick, I think you know. And then we just get a squared. So from here, we can tidy this up and find the amplitudes relatively quickly. So, as you probably suspected, 2 pi cancel out really fast. Cosine of pi gives us -1, minus cosine of 0 gives us 1, so that's going to lead to a -2 that we see there. And then we see that we get our scattering amplitudes. Pretty darn easy, all things considered. And now we can find, from the scattered amplitudes, we can find the differential cross-section. Again, reference our old friend, equation 10.14. And we just need to find the magnitude or the absolute value squared. So that gets rid of this minus sign. And then we just square everything. So just leave it as such. Not that hard. Now from here, we need to find the total cross-section by integrating this differential cross-section, as we had showed previously. So again, we have our phi and our theta. Easy enough, that gives us our total. So if we plug in our differential cross-section, oh no, we got something pretty easy. No angular dependence at all. So we can simplify this pretty quickly. Again, like I said, there's a lot of algebra here. None of it's terrible, but it just takes up a lot of board space, so it's in the PDF if you want it. Again, we see that we end up with a 2 pi minus 0, negative cosine pi plus cosine 0 because it's a negative that we couldn't cancel. Once we plug everything in, we see 2 pi, negative makes a positive, so then we end up with 1 plus 1, so 2, hence the green 2 up there. That allows us to put this purple 2 into this, and we can leave pi outside, so our total scattering cross-section is pi times 4m alpha over h bar squared times a squared all squared. Not that bad. But if we want to solve this for arbitrary energy levels, much like we're told, equation 10.88 gives us the amplitudes, but in terms of theta only, and we see that that's, approximately, thanks to spherical symmetry, r times the potential as a function of r, and then sine kappa r, not k, but kappa. I keep getting that wrong in my own head, so bear with me. So from here, well, before that, let's note that the other ones use just angles. Now we're using the radius only. So we kind of have that baked in, but let's go ahead and execute this integral. All right, so plugging in our potential. Once again, all we see is that we have a delta function here with the constant. Constant goes out front. We need to evaluate the integrand at the shifted value, so that's what we have here. And we find that this the amplitudes are -2m alpha over h bar squared kappa, then a sine of kappa a. So again, not too bad, but how does this relate to what we found in part A? Okay, and that comes into part C where we want to have a comparison to verify. Okay, so with the comparison now in order, let's first compare the results between the two parts within this question. In this case, we wish to show that the part B reduces to part A in a low energy regime, not just arbitrary energy. And in this regime, we're told that Ka is much less than 1. So from equation 10.89, which relates kappa to K, we see that if kappa is equal to 2K sine of theta over 2, multiplying both sides by A allows us to put that in there. And so we see that kappa A is much less than 1. And if this is true, then we know that we can approximate the sine kappa A with the small angle approximation and get out that this thing here, kappa A is much less than 1. So this kappa A is just equal to kappa A thanks to small angle. So substituting that in, we see that kappa and kappa cancel, which is very nice. And then we have AA squared. So, look at this. Our scattering amplitudes are actually the same. And that's pretty darn cool. So that is a nice verification of what we have going on here. But now moving on to the comparison with problem 10.4. In this problem, we were using a low energy regime, and the results were f of theta equal negative a beta over 1 plus beta. But here, beta was equal to 2ma alpha over h bar squared. And in this regime, the approximate condition would be that beta is much less than 1. And this holds because the scattering amplitude over A is a measure of the relative size of the scattered wave. And in this interaction, within the interaction region, remember we had a couple different regions. So applying this condition here, well, if beta is much less than 1, then our denominator here, that's going to go away to 0. So we don't care about it. We go ahead and mark that. That's going to go away, leaving us with just 1 down here. And then from there, we get negative a beta, which if we just plug in beta, we get the same thing. Notice that a and a make a square, and that's exactly what we had in part A. So that's really darn cool to see that we can translate the condition based on the physical phenomena and get the same result, and that allows us to conclude this problem. So as annoying as all these problems are, when taken together and looked over a broad scope, we see that we're trying to show that all these puzzle pieces actually do interact and hold the same thing, even though it doesn't look like we have the puzzle piece oriented well enough to fit into the spot we need it to go in. So that gives you another perspective, and it's really cool. All right, so that was fun. A little more of the algebra heavy and calculus heavy, maybe not much into physics heavy, but again, if we look at it in terms of puzzle pieces, putting them in the orientation they need to actually go into the slot they're meant for, and making sure that the puzzle stays consistent, that's really darn cool. Share this with a friend who's also curious about science, and let's grow this learning community together. I think we see now that learning is not what it used to be 40, 50 years ago when everyone just had to sit at a desk for 12 hours, stare at a textbook until it made sense. Now we have a lot of tools at our disposal, but sometimes learning those tools takes away from learning the material, so we have to have a balanced approach here. And so I really thank all the supporters to help me guide that intuition and the balance to keep that on par for optimized learning and giving new perspectives. especially the patrons who have been in my Instagram messages telling me how they feel about things and what we could do to optimize this whole process. And anybody who comments on the videos with ideas, definitely thank you, because your feedback makes this process better. And if it's better, it'll help more people. So if that's our goal, let's keep pushing forward and keep learning, because this stuff is really cool. Hopefully in 3 years, we'll look at this and be like, that was really cringy and we could do better, and we have done better, and we can look back with pride. And that's the whole goal moving forward. So thank you again for all the people who made that mission possible 2 years ago and just kept it running till now. Definitely can't do this without you. So thank you, thank you, thank you. Books, notes, and other reference materials are found below or on the PDFs with the Patreon page. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.